All right, so here's class number 6, and we're going to do sample problem 3.1. But we're going to do it a little bit differently than the book treats it. Specifically, my reasoning behind this is to try to introduce the standard approach that we will take for most problems. Whereas they're trying to incrementally introduce the idea of the equivalent moments. And they have a few things in here that I don't think are, they're interesting, but they're in the book. You can read them, but I think they're distracting from what we really want to do. So let's, instead of what they're saying right here, let's determine the moment that's created, or the moment that would need to be applied to this for this to be in equilibrium, right? It'll actually be in the opposite direction of what's shown in the book, because they're putting an equivalent moment where we are about to find the sum of the moments. And I'm going to show you this in two different ways, two different approaches, and I think I'll actually even show you okay, so I'll do the same thing for sample problems 3.2 and 3.3. In sample problem 3.3, we actually have 3 separate ways that these are all going to be the same. So I'm going to draw my FBD, and I'm going to do it correctly, right? So my FBD, I'm going to show this is X and Y, and now I'm going to introduce that little guy right here. What we're doing with this little coordinate axes is we're defining what positive is. That's because sometimes we might want to like change it around, or in some situations. Now we're going to pretend like gravity doesn't exist here, so we're not going to worry about it. Or maybe this is in the horizontal plane. So here's the applied 100-pound load onto here. And now I'm going to put my reactions on here. We have to have a reaction in the Y direction. I might even be tempted to put one in the X direction, even though I know it's going to be 0, Rx. And now my reaction, I'm going to have a moment reaction. In order for this thing to balance out, the sum of the moments about that point O must be equal to 0. And these are the sum, in this equation here, that MO, that means all of the moments about here. But it may be a bit confusing sometimes, is that what I put down here is a variable that's included here, which is actually the reaction moment that would be placed onto here. Now, by default, it's often good to just choose, if you don't know the direction of a reaction, to choose it in the positive. Right? So actually, maybe that guy, if that was true, I should have put him this way right here, right? Rx. So this moment that I'll place right there, and maybe I need to stop doing this or change it a different way. I'll just call this M, right? So M is just the reaction moment. I'm not going to give it like an MO because I don't want it to be confused with this. This right here, as stated, is a statement that says all of the moments must equal 0. This guy right here, he's a particular moment. He's the reaction moment, right? So, and he is about O. But I'll just write it right here, M, for the time being, to try to keep that separate. So let me get rid of him. He's in the way. So as I alluded to in the lecture portion of this, we want to, in order to find a moment, we want to take the distance D, that's right here, that is perpendicular to the line of action, right? So we want to extend the force and then find a distance that is perpendicular to there. So if we do that and we proceed through here, first off, I will include the moment, this M, which is the reaction moment. Right? That's a particular moment. That could be like maybe there's a shaft you don't see that's being placed right on here. Or maybe it's welded down here. We want to figure out what the moment inside the weld is. Or maybe there's a shaft, and of course we're free body diagram, so we've cut the shaft here, and somebody's got their hand on this, or like maybe a crank or something. Maybe there's a crank on this, and somebody is turning the crank And in fact, it actually has to go the opposite direction for this to balance out, right? So they're turning a crank. I just did the exact same wrong thing. No, it was correct. Yeah. So maybe they're lifting up on this crank to try to and balancing out that 100-pound force. That's the concept and the idea. So that M is an external thing that's applied, this reaction. And so now what's this force? What kind of moment does this force go? It goes clockwise, right? Taking a look at ... This dotted line right here is what I'm trying to emphasize, that 100 pounds, you'll see, is going to try to go clockwise about this point. Therefore, it's a negative, and it's 100, and it's times D, and that equals 0. Right? So what is D? D in this case would be, D is going to be equal to 24 times it's going to be the cosine of 60, right? And I started to write the sign, cosine of 60 degrees, right? So M, that reaction moment, is 100 times 24 times the cosine of 60, and that ends up equaling 1,200 pounds, right? And by the way, I always write out this way first. I don't just write this. Right? We want to make sure that we emphasize, because we could have several moments going on here. We could have several other forces. There could be many other things that are going to enter into this. So in order to keep track of stuff, we're going to actually write it out the same way here, and then we're going to make the transition and set M equal to this. I know it seems like a kind of very fussy, but it's an important distinction. And so anyway, we would answer with M, the reaction moment was 1,200 pounds. Oh, excuse me. I made it bad. Inch pounds is the units. Inch pounds. And in presenting this, we would say this. Okay, and now this is the reaction, right? And I'm often, though, will make it confusing, because I will write this equation up here, but this moment I'll also call MO quite often, because we want to make some distinction about what's a moment about, right? And then we also would want to say the sum of the forces, I just want to emphasize, are equal to 0. In the y direction, we would do that, and this would be very simple, right? Simplistic maybe, that we would say Ry, and then we look at the forces on here are minus 100, right, equals 0. So Ry, the reaction force, is 100 pounds upwards, right? Now I could do this in a whole different way. So maybe I'll erase some stuff. Okay. This could be done in a whole separate way. And it's useful to think about it in these terms, right? So, erasing everything and showing you the other way that we could apply this. I want to get rid of all this. Maybe I should just start with a fresh page, right? All right. Instead of taking the force as shown, we could say that we could break it instead into these components. And we could say that this was, okay, and looking at the way that this is divided up right here, let's see, maybe this right, okay, so right, if we're going to make a little parallelogram here, I'm putting it as dashed because we don't want to double dip. So I'm only putting these loads onto here as they are components that break down into that are aligned with this piece right here. And you would say, let's see, the way that I wrote the thing out is I went ahead and I used this, right? So I went 30 degrees. It just was easier in my mind to do that, so that I would say that this was 100 times the sine of 30 degrees. Whereas this right here was 100 times the cosine of 30 degrees, right? Now, if you take this line of action of this guy, you'll see that we have a D that runs along there. It's actually this length is the entire D. But if you were to try to get what the moment that's due to this 100 times the cosine of 30, you would see that because the line of action continues down through the pivot point, the D for that one is 0. So it's only this force that's perpendicular to the piece that actually causes a moment. So the sum of the moments about O equaling 0, and I should always define what positive is when I write this thing out right here. We would take and look at that and say, well, okay, the reaction is one of the things that's on my free body diagram. And then I see that this 100 times the sine of 30, once again, is going to try to go in the clockwise direction, so it's negative. So this load is 100 times the sine of 30, and it's times D, which I happen to know is 24, equal to 0, and I get M is equal to 1,200 inch-pounds. And I can just go ahead and put that vector on there, and we get the same thing. The real idea here, the big idea, is that you can either take the geometry of the distance right here, or you could try to break the force into components and then take a distance that you already know that can become convenient. It's this alternative thing that's always available, and some problems are going to be easier than others to approach in this way. So once again, I want to emphasize, when you look at the sample, and I encourage you to look at the sample problem and see what they've done, right? They, especially for this first part A right here, they're just taking the equivalent moment. So the equivalent moment is going to be like, what they do is they're going to say equivalent moments. They don't draw it out this way, but they probably should. Is going to say that, like, okay, we have this. Oh, I'll draw another one here. This right here is the equivalent of saying this right here, right? That we could replace the moment that's been caused by this force, right? But this is only moments that we're showing. We're going to show something very similar in a class coming up very soon. But we take this and we can say the equivalent is this guy over here on the right. Just get that idea, right? That we have reactions, which is almost always what we want to try to solve for in real problems. And then we're taking the incremental understanding that they're trying to get in this section. So, don't know if that helps. I think I like it better. But anyway, let's see. We'll discard this and see how much time we took. That was a 13-minute problem.